waveguide. But if you want to reach something like that, it's a bit more problematic. Usually, there's a few schemes that we can use to achieve that level of planarization. First of all, I'd like to explain why you want planarization in the first place. So the main goal is to have a multi-layer design, like this work by Ali Adibi's group. We can have a multi-layer design. We have one layer on the bottom, another layer on the top, and they're connected, coupled vertically, and we can couple the light from the silicon, like we see here on the bottom, to the silicon nitride resonator on top, and we can benefit from each material and its properties. Because, like here, the silicon nitride is more intrinsic, more elastic. It doesn't have this non-linear effects, and you can reach high Q factors, and there's all other kind of benefits of using multi-layer design. Another benefit is just we can have a lot lower fabrication error because due to the position than due to the lithography, because it's very hard to do a lithography of two waveguides with a small gap between them. And even if you do this lithography in the resist, it's very hard to copy it by RE to the silicon beneath. But when you do the position, it's very easy because we can control the position very well. And another benefit is that you have a lot more devices per die. You can use each layer as a different layer to use the device for devices. Oh, I have no idea what I did. Okay. And another big benefit for resonators is that in this scheme, the coupling region between the waveguide and the resonators is hidden from the environment. So it won't be affected by any kind of analyte that goes by and lands on the coupling region. It won't be affected because the coupling region is hidden by this example, an oxide layer. So how we do this planarization? And the conventional method is just to put the oxide on top, and then use a chemical mechanical polarization, which is just a polish with a chemical slurry, and we get a very nice and smooth surface on top. But this method is not that simple because you need a lot of know-how, because you don't want to polish too much, you don't want to polish too little, and it's a bit difficult and it's expensive. It's not that easy to use. Like we in the our university don't have this device, and it's usually made for big wafers and not chips like we use. So we want to think about different alternatives. How can we do planarization? And we saw this work from 1982, 30 years ago, and they suggested to do this method of planarization and achieving this planar design by partially etching the silicon and covering it on the side with nitride. But we try to take this scheme and simplify it a little bit. So we, first of all, also start with what they do. And we do use this LOCOS scheme, but we do it a little bit differently. And what I mean by LOCOS is the local oxidation of silicon. If most of you maybe not very familiar with that, when you just put in the silicon with some cover layer of nitride in an oxidation oven, in a very high temperature oven, and the oxide penetrates the silicon and it becomes silicon oxide. And that's how you can create the boundaries for your waveguide, the resonators, or whatever you want. For this work, it was used for a MOSFET transistor gate or a different other application for electronics and not for optics. Just a funny anecdote, I tried to look for Swami on Google, and that's the first result that you get. So be aware that when you look for this work, you won't exactly see this one. So we talk about how we plan to do how we did our fabrication. And we started with silicon oxide, which is covered with a nitride layer of 200 nanometers. And we do even lithography on top of the design of the device that we want, and followed by an etching. We etch also the nitride, and we etch partially the silicon. How much of the silicon we need to etch? We need to etch about half of the silicon. Because once we put it in the oven, the silicon oxidizes, and we want it to reach exactly the height of the initial height of the silicon over here. So next we put it in the oven, and the silicon inflates, it becomes silicon oxide, and it reaches exactly the level that we want it to reach, exactly as the silicon was here before. And we remove the nitrate on top by just using high phosphoric acid. Okay, next comes the result. This is the sample image of what we got. This is the green is the silicon, yellow is the thermal oxide that we created, and below the oxide that was before, the buried oxide. And we can see on top the AFM scan of the top surface. As you can see here, we have the small bumps on the side. These bumps are due to that we have oxide rising from the bottom and from the side. We have lateral and vertical oxidation, so we create these small bumps. They're quite small, you can barely see them in the same image, but here you can see them, they're about 50 nanometers in height and 100 meters in width. But we believe that we can reduce it even further, create truly flat surface by adding more height to the nitrate layer. We saw different works that by adding a higher, a thicker nitrate layer, it's possible to reduce these bumps, and by raising our oxidation temperature, we can reduce the viscosity of the oxide by 2 orders of magnitude, and to hopefully to make it more flowable and just blend those bumps. But this is for future work. We fabricated disc resonators. Disc resonators, they have a wisp and gallery mode. And I would like to show you what we got. We got a very, very high Q factor for this disc resonators. This resonator has a radius of 30 microns. And the Q factor that we got is 5.3 million. And we have a propagation loss of 0.12 dB per centimeter compared to regular wave bands, it's about 2 dB per centimeter. We compared this work to previous work. This is the highest Q factor that we find on silicon on insulators. The work by Matthew Borselli from Moscow group. You got a Q factor of 5 million. We have 5.3. It's about the same. It's on the highest Q factor we got till this day. I'd like to get to the conclusions. So we proved that we have almost a completely flat top faucet. We have very low propagation loss on use of this platform. And we have a very simple and low-cost alternative to chemical and mechanical polishing of silicon. And I believe that this is a very promising platform for future applications, for modulators, filters, sensors, or whatever you can do with resonator in silicon. Finally, I just want to thank everybody that took part in this work. This is the sign of the article really helped me a lot. And this is my group. I would like to thank you for listening.